Okay, for problem 2, we have a closed piston cylinder device containing air at an absolute temperature of T1 equals 300 Kelvin and specific volume V1 equals 2 meters cubed per kilogram. The air undergoes a power cycle composed of the following 4 processes, and data at each state is included in the table below. So isn't that nice of them? They give us this table here below with all of the different properties for temperature, specific volume, internal energy, and enthalpy at all of these 4 states here. So I'm going to spend some time setting up the problem first before we get into the solution. Again, they want us to set up our equations, our system, and our energy flow diagram, and our assumptions before we get into our solution. So let's look at this list of processes here to make sure we really understand what's going on. And so I've sketched out just a piston cylinder device here so we can try to think about what's happening at each of these different processes. So from 1 to 2, we have isothermal compression from a higher specific volume to a lower specific volume. So isothermal, that means that our temperature isn't changing, and we can see that in our table here. Our temperature is the same from state 1 to state 2. But since we have compression, we are going to have this piston moving down to a new location down here, which is why our specific volume is decreasing from state 1 to state 2. So the piston moves down, but the temperature does not change from 1 to 2. And then from 2 to 3, we have heat transfer at a constant volume until temperature is equal to 1500 Kelvin. So now this piston is still down here at state 2, and then as we are moving to state 3, it stays in the same spot, but then we're adding some heat into the system. So we'll have some Q going into the system so that our temperature changes and increases to a higher temperature, but our specific volume is staying the same from 2 to 3. And then 3 to 4 is an isothermal, again, expansion this time until V4 equals 2 meters cubed per kilogram. So now the temperature is staying the same, but our piston is moving back up here. And actually it's going to move to the exact same spot that it was at state 1. You see that we're at 2 meters cubed per kilogram again, so it's going back to its original spot back up here. But now our temperature is staying the same from 3 to 4. So that's 3 to 4. And then 4 to 1, we have to complete the cycle by going back up to state 1. So we're going back up to state 1 like this from state 4. And that's just going to be heat transfer at a constant volume again back to state 1. So our piston is again still sitting here at the top, but our temperature needs to return to the value that it had at state 1, so then we're going to be taking some heat transfer out of the system. Okay, so we have a lot of different things going on, but hopefully that makes sense. So let's draw out our system first. So I just want to focus on the air inside the cylinder as our system. Right? It doesn't make a lot of sense to include the piston. The only thing that we're worried about is this air. So I'll say that the system is going to be the air inside the cylinder. And it makes sense to just focus on the air because all of this stuff that they give us in the table here is the properties of the air. So that's our system, and then we have a lot of different heat transfer and work processes. So we have one instance where we're adding heat transfer in, but then another instance where we're taking it out. So I'm going to draw an arrow like this so that it's going both ways throughout this power cycle. And the same thing with work. From state 1 to 2, we bring the piston down, so we're doing some work on the system, and then from 3 to 4, we're bringing the piston back up. So we're doing work out of the system. So I'm going to draw these work and heat transfer arrows pointing both ways here. And then for assumptions, well, if you did the fall 2018 exam 1, which is the same year that this one is, then hopefully you're pretty comfortable with piston cylinder problems by this point, and we know what kind of assumptions that we want to make here. So first, it tells us in the problem statement that we have a closed piston cylinder device. So since this system is closed, that's going to mean that our mass is going to be constant inside the cylinder. So the amount of air in the cylinder is not changing. It's getting compressed as this piston moves down, but the amount of air isn't going to change since this is a closed system. Okay, another one that we typically make is that we have a quasi-equilibrium process. Quasi-equilibrium process, which again basically just means that we can say that the air inside this cylinder is always at a state of equilibrium. So if we wanted to report the temperature for the air, we could say it's the same at this point here that it is over here. We just report one value for temperature at each state. And this process is happening slowly, so we can always just report one value for each of these properties here. We don't have to worry about any differences from different points in our system. So quasi-equilibrium. And then they don't give us any information about changes in kinetic or potential energy here. So we're going to say that changes in kinetic and potential energy are equal to 0. And then we usually, if they don't give us any information about friction, we like to say that we're going to neglect friction in this problem, which means that as this piston is dropping down to a new state down here, it's not going to be rubbing against the walls at all. It's going to be moving smoothly. Another thing here is that we have air inside our cylinder. So for us, it's going to make a lot of sense here to assume that air is an ideal gas. So we're going to say that air is an ideal gas. And we're getting information about temperature and specific volume, so hopefully we can see that maybe there's some ideal gas law stuff coming down the road, because these things are both included in ideal gas law along with pressure. And that's a pretty good start. I guess we could also say that there's not going to be any other work besides boundary work. So I'll say that there's no other work besides boundary work. So the only work we're going to have to worry about is the work related to this piston as it moves positions in here. We don't have any other external work with any shafts or anything like that. So the only work we are going to focus on is the work done by this piston and the work done on this piston by this air. So that's a pretty good start to setting up our problem. And now I will move into the solution for part A. Okay, let's move on to our solution for part A, which asks us to show the cycle on a PV diagram, label the axes in the 4 states, show the lines of constant temperature, and indicate the process directions with arrows. So our final goal for this part of the problem is to draw a PV diagram. And remember, we have this nice table here where they give us a lot of the different properties, including specific volume at each of the 4 states. So we already have the V in our PV diagram for each of the 4 states, so we're halfway to being able to draw the points, but we still need the pressure at each of the states, and they don't give us that in this table. What they do give us, though, is the temperature and the specific volume. And if we remember that the system that we're dealing with is air, and we're assuming that air is an ideal gas, we can use the ideal gas law, which brings together temperature, specific volume, and pressure. So we can use that to solve for the pressure, but we can only do that because we're dealing with air here. If we had steam or water or something else inside of our cylinder here, then we would not be able to use the ideal gas law. So we'll use the ideal gas law to solve for pressure and then get all of our points and then plot them. So let's scroll down to the equation sheet and look at the ideal gas law. The ideal gas law is right here, but it's in a different form. It's in P capital V equals M RT. So if we just remember that specific volume, little v, which I'll draw with this tail here, is equal to total volume, capital V, divided by the mass of the system, then if we move this mass over to the other side in this equation, then we get the form P times little v, specific volume, is equal to R times T. Again, just moving this mass over to the other side. And so we already have specific volume, we already have temperature, and then this R, we have to use the R specific for air, and we can solve with this equation because they give us the molecular weight of air in the problem, and then this R bar is just from the equation sheet down here. R bar is equal to 8.314 kilojoules per kilomole Kelvin. So with these two equations, we can solve for pressure. So let's go write those down in the equation section. So we will have P times, I'll just write it in this form, PV equals RT, and R equals R bar over the molecular weight of air. And again, that is given right here. It's 28.97 kilograms per kilomole Kelvin. Okay, so we can just use these two equations to solve for the pressure at each state, and then we'll be able to plot our points. So we'll go down there and write it out. First, I'll just solve for this R in case you forget the R value for air. It's just R of air is equal to that R bar, which is 8.314 kilojoules per kilomole Kelvin, divided by our value for molecular weight, which is 28.97 kilograms per kilomole. So here, just the kilomoles will cancel, and then we'll get our answer of 0.287 kilojoules per kilogram Kelvin. Okay, so that's our R value that we will use in this equation to solve for pressure, and then we can just rearrange this equation for pressure by moving specific volume over to the other side, and we can do that at each of the states. So at state 1, we'll have P1 is equal to RT1 divided by V1. Again, that's just moving this V over to the other side and solving for pressure. And so this will equal 0.287 kilojoules per kilogram Kelvin. That's our R times our temperature, given in this table as 300 Kelvin. 300 Kelvin, all divided by our specific volume at state 1, which is in our table here as 2 meters cubed per kilogram. And then if we just plug that into our calculator, we should get something like 43 kilopascals, doing a little bit of rounding. And so we get kilopascals because we're using this version with kilojoules. So make sure you don't get your kilopascals and your pascals messed up. So just if we have kilojoules, we'll end up with kilopascals. And then we just do the exact same thing at all of the other states. I know it's kind of a lot of calculation, but that's all we need to do. So I'm not going to write out all of the different values here, but we would do the exact same thing for P2. P3 is equal to R times T3 over V3, and then P4 is equal to R times T4 over V4. And so again, we have R in each of these cases. It's still going to be the same 0.287. And then we have the temperature and the specific volume from our table up here. And so we just plug in all of those values, and again, I'm not going to write it out just for saving some time, but P2 should be around 430 kilopascals. P3 should be around 2150 kilopascals. And then P4 should be around 215 kilopascals. So that's just doing some rounding, but these are the values that we should get for pressure. And now we have everything for our PV diagram. So we can start to draw out our points on the PV diagram. And then we just need to figure out how to connect them. So I have a PV diagram sketched out down here, and we'll just go in and start to label our points. So state 1, we have the lowest pressure out of these 4 pressures here. So we're going to be at the lowest value on our graph. And then specific volume, we start out at 2 meters cubed per kilogram. But here you see we only have 2 different combinations of specific volume. We have one at state 1 and 4, and then at states 2 and 3, we have a different one. So we're only going to have two different locations on our x-axis here. So we start out to the right, at our rightmost location, at V1, but that's also equal to V4, remember from our table, that's equal to 2.0 meters cubed per kilogram here. And then our pressure, P1, again, we're starting at the lowest value, so I'm just going to draw it around here. P1 equals about 43 kilopascals. So we draw the intersection of those points around here, and that is going to be state 1. So now state 2, remember we have a compression for state 2, so we are moving to a smaller specific volume value, so we'll be moving to the left on our chart, and then we're increasing in pressure from 43 to 430 kilopascals. So now we move to this other location on the left, which will be our V2, but that will also be equal to our V3, and that is equal to 0.2 meters cubed per kilogram. And then at P2, we jump up to about, we'll draw it somewhere up here, P2 equals 430. So again, you don't have to make everything perfectly accurate with your spacing and all these things, but just try your best to show the trends accurately, and that's all you can do. But our point 2 will be somewhere around here. We'll call this state 2. And then our next process is a constant volume. See, so we stay at the same specific volume, constant volume heat addition, and we move up to a higher temperature, which means we move to a higher pressure as well. We move from 430 to 2150. So we just had this as a straight line up, and then we're moving to our highest pressure on the chart. So I'm going to draw it somewhere around here, and this will be P3. And so again, this is just a straight line upwards since we are staying at a constant volume in this process. V2 equals V3. And then we drop again to somewhere in between these two pressures at 215, but then we're at our same specific volume value as well. So we'll drop somewhere maybe around here and end up at a point somewhere around here at state 4, and this is P4 should be equal to 215 kilopascals. Great, so now we have all of our points labeled on our chart, and then we need to connect them. So for these states, for these two, it's easy because they're at a constant volume process, so it's just going to be a straight line, and same for 2 to 3. Since it's a constant volume process, you just connect them with a straight line because we're not moving to the right or left at all on our chart. So obviously we're going to go from 4 to 1, and then from 2 to 3, and those will both be connected with a straight line. And then we need to figure out how to connect 2 and 1, and then 3 and 4. But we've done this, hopefully we've seen this a little bit in the course. If you don't remember how to connect these things, an easy way to do it is to try to get some equation for pressure as a function of a specific volume. Actually, that's exactly what we did in order to solve for pressure here with all of these different steps in the equation here. We got pressure is equal to some stuff times 1 over specific volume. So I'll just write that out here. We got pressure is basically what we learned from solving for pressure is that it's proportional to 1 over specific volume. And what that means is, if we had something like y equals 1 over x on a normal chart, then we would have some sort of curved downwards line like that, and that's exactly what we should expect for these lines that connect these other states. And so if we instead found something like pressure is equal to volume, then we know that on a graph that would be a linear, something like that, like y equals x. But since we have this relationship for P is proportional to 1 over V, we will get these curved lines connecting these points. So from state 1 to state 2, we should have some sort of, maybe I'll draw that a little bit more curved line like that. And so we connect 1 to 2 with a curved line like that. And you can see we have a little bit of a steeper curve like this, connecting state 3 to state 4, and we will point from 3 to 4. And remember, these curved lines here are our lines of constant temperature. So everywhere along this line, we are at constant temperature because from state 3 to state 4, we have a constant temperature expansion. And then from state 1 to state 2, we have a constant temperature compression. So everywhere along the line from 1 to 2, we're going to be at this temperature. And everywhere along the line from 3 to 4, we're going to be at this constant temperature. So we will just draw that in maybe like this. T1 equals T2 equals 300 Kelvin. And then over here, maybe you can say T3 equals T4, which should equal 1500 Kelvin. So this will be our final answer for our PV diagram. Should look something like this. Again, maybe yours looks a little bit different with just the exact placement of all of these points and all of the lines and how you draw them. But as long as you get the general trends correct, then that's all that matters. Okay, for part B, they want us to calculate the specific work and specific heat transfer for each of the 4 processes in the cycle and report our answer in kilojoules per kilogram. So here they want us to calculate specific work and specific heat transfer for each of these 4 processes in the cycle. So we're going to end up with 8 total answers, and it's going to be a bit of a longer problem. But how are we going to tackle this? Well, for specific work, we need to remember that we made this assumption here that there's no other work happening besides boundary work in this problem. So we don't have any external work input from any shafts or any springs or anything like that. The only work we have to worry about is the work that happens due to the change in volume from this piston moving down and compressing the gas, and then the gas expanding and moving the piston back up. And that boundary work, we know how to solve for it. That's our PDV work that we have in our equation sheet. And then heat transfer, how can we solve for that? Well, if you see heat transfer and work in the same equation, in the same sentence here, we should automatically be thinking about first law because that's the equation that brings together work and heat transfer and changes in energy of the system, specifically internal energy, which we have here in the table. So let's scroll down and look at those equations that we're going to need. So here on the equation sheet, this is our boundary work equation that I mentioned, our PDV equation. The form that they have it in here as our total work, capital W, and this integral is with respect to total volume, capital V. But if we divide both sides by mass, they're asking us for the specific work, not the total work. So if we just divide both sides by mass here, we can come up with a form of the equation. Specific work is equal to the integral of P with respect to specific volume, this little v here. So that's the equation that we're going to use because we have information about specific volume in our chart, and then we solve for pressure as well. So we can use that to solve for specific work. And then for our first law equation, that's the one we see right here. It's written in the differential form in the equation sheet, but we know that we have a closed system, so we don't have any mass coming into the system, so this whole term will cancel, and there's no mass coming out of the system, so this whole term will cancel, and then we're left with a much more simplified form. And it's still in differential form here, so we can integrate each of the terms here and get rid of the time dependence. And if we do that, then the ddt goes away, and then these dots will also go away. So we'll get a form that looks like delta E, the change in total energy of the system, is going to be equal to the total heat transfer minus the total work. Then remember, we can break up our changes in total energy into our changes in internal energy, plus our changes in kinetic energy, plus changes in potential energy. But here we are neglecting changes in kinetic and potential energy because they don't give us any information about that. So we're left with only changes in internal energy. And then similar to what we did for our PDV equation, if we divide both sides by mass, then we can get things in terms of specific quantities instead of total quantities. So if we do this, then plugging in our delta U is equal to delta V we get delta E, changes in specific internal energy should be equal to the specific heat transfer minus the specific work. And we have these quantities in our table, and then we have our equation over here to solve for this specific W, and then we can use that to find our specific heat transfer for each of the cases. So let's go write those in the equation section. Those are the forms of the equations that we want to use. So we have specific work is equal to the integral of P with respect to specific volume. And then we also have our first law, changes in specific internal energy should be equal to the specific heat transfer minus the specific work for any process here in our cycle. So these are the equations that we want to use. And then we need to basically just evaluate these equations at each of these processes here. So we can just kind of write those out to start. I will start with just process 1 to 2. So looking from 1 to 2 on our PV diagram, that is from right here to right here. And so our delta U is just going to be U2 minus U1, because we do final minus initial, and then 2 is our final state and 1 is our initial state here. So that should be equal to the specific heat transfer from 1 to 2 minus the work from 1 to 2. And if we look at our table here, we see that the internal energy is the same from state 1 to state 2. And so the change in internal energy here is going to be 0 because these quantities are equal. So these terms will also cancel out here. And so what we are left with is just that the heat transfer from 1 to 2 should be equal to the specific work from 1 to 2. And then how do we solve for our specific work? That's our PDV equation. So we can come down here and say that our work from 1 to 2 is going to be equal to the integral from V1 to V2 of P with respect to specific volume. So if we want to actually evaluate this integral, we need some form of pressure in terms of specific volume. And we did that earlier in the problem to find our pressure values at all of the states for part 1. What we found was we were able to rearrange this equation up here, our ideal gas law, by moving specific volume over to the other side and then solving for pressure. So if we write that form out, that form is pressure is equal to R times T over specific volume. So we can take this equation and just sub this P into our pressure in our boundary work because that has a specific volume in it. So that's what we want to do here. So continuing with this integral, we're going to get the integral from V1 to V2 of P, which is RT over V times dV with respect to specific volume. And then here, our RT is actually a constant because our R is a constant for the gas, and then T, we're along this line on our PV diagram here from 1 to 2, which is an isotherm. So everywhere along this line, we are at a constant temperature of 300 Kelvin. So this temperature isn't changing with respect to volume, so we can move this whole quantity out front here. That will be R times T1 or T2, they're the same, so it doesn't matter, times this integral of 1 over V dV from V1 to V2. And we need to remember that this integral is evaluated as natural log. So this is going to be equal to R times T1 times the natural log of V2 over V1. Make sure you remember this integral from your calculus class. Integral of 1 over x is just natural log of x. And then we evaluate it from 2 to 1. So you put 2 in the numerator and 1 in the denominator. And so we can just simply plug in our values here. Keep going. Work from 1 to 2 should be equal to R, which we solved for in part 1. If you don't remember, we use this equation, R bar over the molecular weight of air, which they give us up here, but if you don't remember, it is 0.287 kilojoules per kilogram Kelvin times our temperature, which is 300 Kelvin. Here at state 1 and state 2, remember it's just 300. You can see it in the table as well. The temperature doesn't change from 1 to 2. And then this is going to be multiplied by the natural log of V2 over V1. So we can just get those from the table as well. V2 is 0.2 and V1 is 2. So the ratio of those, well, I'll just write them out, 0.2 over 2.0. And if you plug this into your calculator, you should get the total work should be equal to negative 198 kilojoules per kilogram, the specific work. So this is going to be our answer for work 1 to 2. And then remember, we have the heat transfer is just going to be equal to that work value as well. So then we'll also get our heat transfer from 1 to 2 should also be equal to the same value with the same sign, negative 198 kilojoules per kilogram. So this will be our answer for the process from 1 to 2. And if you want to check real quick, you can think about the sign and make sure it makes sense. So for work, we get a negative sign. And that's because we have a compression process. This piston is doing work on the gas. So since there's work being done on the system, we know that that's negative work because we typically say that it's positive if the system is doing work. But since this piston is doing some work to compress the gas, we have a negative work value. Okay, now we can do the exact same thing from 2 to 3, but I also want to remind you that we are evaluating this equation as an integral of PDV, and we have a PV plot that we did in part A, so you can also see visually what this integral should look like on the graph here, because we know that the integral should be the area under the curve. So from 1 to 2, this is the area under the curve that we just found in part A. You know, this work was equal to a negative value because we're going from right to left here. But in this process from 2 to 3, we're staying at a constant volume and we just have a straight line upwards. So there's no area under this curve from 2 to 3 because it's a straight line upwards. So that integral, you can't evaluate it. That will just be 0 because there's no area under that curve. So we can solve for the work from 2 to 3 without even doing any math because we can see graphically that there is no area under the line from 2 to 3. So our work from 2 to 3 should just be equal to 0. And the same thing is true for our process from 4 to 1 because this is also a straight line, so there should be no work there. I'll write that down here as well. Our work from 4 to 1 should be equal to 0. And so those are going to be part of our answer as well. And then we can just do our first law again to solve for heat transfer from 2 to 3. So writing this out again, we're using the same form of first law that we had here, but now we're doing it from 3 to 2 instead of from 1 to 2. So we are going to have U3 minus U2 should be equal to this heat transfer from 2 to 3 minus the work from 2 to 3. Remember, we just found that that work is equal to 0, so this term will cancel out. And so we are just going to get that our heat transfer from 2 to 3 should be equal to U3 minus U2. And we have those values in our table up here. U3 is 1205 and U2 is 214.1. So we have 1205 kilojoules per kilogram minus 214.1 kilojoules per kilogram. And so this should get you a value of a positive 991 kilojoules per kilogram. So this is going to be our heat transfer from 2 to 3, and it's positive. Make sure that makes sense with the problem. Remember, from 2 to 3, we have here heat transfer into the system at a constant volume because we're increasing this temperature from 2 to 3. So we expect a positive value for heat transfer because we have positive heat transfer if it's being done into the system. So that makes sense. Then from 3 to 4, we want to follow the similar process. So we can write out our first law for 3 to 4. It's going to be U4 minus U3 should be equal to the heat transfer from 3 to 4 minus the work from 3 to 4. And then again, similar to what we had up here for 1 to 2, we see from 3 to 4, we have the same value for internal energy. So there's no change from 3 to 4 in the internal energy. So the left-hand part of our equation is going to cancel out, and it's going to be equal to 0. And what we're going to be left with is our Q from 3 to 4 should be equal to our work from 3 to 4. And then taking the same approach, we can just use our PDV equation to find this work from 3 to 4 as the integral from V3 to V4 of our, and we want to use this same equation for pressure as RT over V, the same one that we got from our ideal gas law up here. So we want to plug in R times T3 or T4 and then V. So we have RT over V, and this integral is taken with respect to specific volume. And again, this RT value is going to be a constant, so we can bring it out front because the temperature is constant all along this isotherm from T3 to T4. Everything happens at 1500 Kelvin here. There's no change in temperature, so this value is a constant. We can pull it out front. So this is R times T3 or T4 integral of 1 over V dV. And again, that should be natural log. So we're going to get R times T3. Again, this is from V3 to V4. So now for the natural log, we put this one in the numerator and this one in the denominator. Times natural log of V4 over V3. And then we just plug this into our calculator, plug in our values. We'll get work from 3 to 4 should be equal to, R should be 0.287, again, kilojoules per kilogram, times temperature. Now it's at 1500 Kelvin. You can see it from the table as well, but it's 1500 Kelvin this whole time from 3 to 4. And then times natural log of, now at V4, we have 2 meters cubed per kilogram divided by 0.2 meters cubed per kilogram. So 2.0 meters cubed per kilogram divided by 0.2 meters cubed per kilogram. And if you plug this all into your calculator, you should get, this should be equal to positive 991 kilojoules per kilogram. And this time our work is a positive value. You know, from 1 to 2, we found that we had a negative value because we were doing a compression on the gas. But now from 3 to 4, the gas is doing an expansion and moving the piston back up to its original state. So we should have a positive value for work. And we are almost there. We just need to finish up by finding our heat transfer from 4 to 1. So again, we found that this work from 4 to 1 should be 0 because we have a straight line on our PV diagram and it's a constant volume process. So there's no work being done during a constant volume process, but we do still have heat transfer. And we can just find that by writing out our first law once again. So now be careful. You want to do U1 minus U4 because 1 is our final state and 4 is our initial state for this process. So we want to have 1 as final and 4 as initial, even though we usually have the higher one first here. So U1 minus U4 should be equal to this heat transfer from 4 to 1 minus the work from 4 to 1. But again, this work is 0, as we just found from our PV diagram. And so we are just left with our heat transfer from 4 to 1 should be equal to our internal energy at 1 minus our internal energy at 4. And we can just get those values again from the table. U1 is 214.1 and U4 is 1205. So we should get that our Q from 4 to 1 should be equal to, sorry, that was 214.1 kilojoules per kilogram minus 1205 kilojoules per kilogram. And this should be equal to negative 991 kilojoules per kilogram. So this will be our final specific work for, specific heat transfer for our process from 4 to 1. Okay, so a lot of calculation for this one. Again, we can do a final sign check on this heat transfer from 4 to 1. We get a negative sign here, and that makes sense because from 4 to 1 we have heat transfer at a constant volume back to state 1, so we're going from a higher temperature down to a lower temperature at state 1. So in order for us to drop in temperature like that, we need to lose some heat going out of the system. So it makes sense that we have a negative value for heat transfer. But yeah, this is the final work for this one. Definitely a longer problem, but hopefully it went well for you. Nope, but I almost forgot to write out our heat transfer from 3 to 4 should be equal to, we found that our heat transfer should be equal to our work from 3 to 4, and we found that our work was 991, so our heat transfer should be also positive 991 kilojoules per kilogram. So this should be our final answer for part 4. We have, for part B, we have 1, 2, 3, 4, 5, 6, 7, and 8 final answers. So make sure you keep track and make sure you have all of your answers there. Now we can move on to the final part of this problem, which is part C, and that asks us to determine the thermal efficiency of the cycle and report our answer in percentage. So part B that we just did was pretty long. We found all of these values for work and heat transfer for each of the processes in the cycle. But now part C is pretty nice because we can just plug those values for work and heat transfer into our equation for thermal efficiency. We just need to figure out which values we're going to use for work and heat transfer. But we are going to use our equation for thermal efficiency that we use for power cycles, since it says we have a power cycle here. So let's scroll down to the equation sheet and look at which efficiency equation we should use. So here in the equation sheet, we have this whole section for efficiencies, but we're not worrying about any turbines, compressors, pumps, heat exchangers, nozzles, refrigerators, heat pumps, none of that stuff. And we want to use this equation here for the thermal efficiency of a power cycle. And the way we define that is by the magnitude of the net work done by the system divided by the QH, which is the heat transfer into the system. So we have to put some heat, we have to pay for this work by putting some heat into the system, and as a result we get some positive work done by the system. So this is the equation we want to use, and I will write that down in the equation section. So we have eta TH should just be equal to the net work done by the system divided by the heat transfer into the system, which is QH. Okay, so now I erased the arrows from our energy flow diagram because now we know the direction of all of the work and heat transfers that we have throughout these processes. So we can just kind of draw those with the arrows in the direction that they occur so that we can have a better intuition about what to put for our QH and our work net values. So starting with work, we have some net work out of the system, which is going to be equal to the positive work we get from 3 to 4, because we have positive work from 3 to 4, but then 1 to 2, we have negative work, because from 1 to 2, it's a compression process, so this piston is doing work on the gas, but then 3 to 4 is an expansion where the gas is doing the work, the system is doing the work. So we're going to subtract off that work from 1 to 2. I'll just say the magnitude because we found it here to be negative. So we're subtracting the magnitude of this because this is taking away from the total work that we're able to do with the expansion process. And then for heat transfer, we have some heat leaving the system at the process from 1 to 2 and also from 4 to 1. We get negative signs here. So the magnitude of Q out is just going to be equal to the magnitude of Q from 1 to 2 plus the magnitude of Q from 4 to 1. But then at the other processes from 2 to 3 and from 3 to 4, we have positive values of heat transfer going into the system, so we can write that our Q in, and all of these are going to be positive, should be Q from 2 to 3 plus Q from 3 to 4. And so the net work, what we want to plug in is exactly this network value. It's the positive work that we get from the expansion minus the negative work that we get from the compression. And then the QH is the Q in that we get, a combination from the heat transfer from 2 to 3 and from 3 to 4. Right, because we have to put some heat into the system here in order to get some net positive work out of the system, and that's how we define our thermal efficiency. So now we can just write that down. So now we get eta TH is equal to magnitude of net work divided by QH. But like we said here, this net work is going to be our work from 3 to 4 minus the magnitude of the work from 1 to 2 here. And then our QH should just be our Q in, because that's the amount of heat transfer that we need to put in order to generate some work out. So then our work net is going to be work from 3 to 4 minus that magnitude of work from 1 to 2. And then all of this is divided by the total heat that we put in, which is Q from 2 to 3 plus Q from 3 to 4. So now we can just plug in our numbers, and we get 991 kilojoules per kilogram minus the work from 1 to 2, which is 198 kilojoules per kilogram, all divided by Q 2 to 3 is 991 kilojoules per kilogram plus 991 kilojoules per kilogram. And so if you evaluate this in your calculator, you should get about 0.4, and they want it in percentage, so our final thermal efficiency should be about 40%. And this will be our final answer.